and present the webinar. Thank you so much, everyone.
Thanks very much, Professor Reddy. I also know Krishna for a long time. It's my inspired like a leader that inspired me to look in more depth into research. Yeah, I appreciate this opportunity that you put together to allow communication to happen, to inspire each other. So let me share my screen. So can you see my screen now?
Yeah, I can see it.
Okay, thank you. It's related to the theme, this seminar series about sustainability resilience in the geoenvironment. So I select this one. So multi-scale sensing and simulation for soil erosion and georisk mitigation. So this part of related to my National Science Foundation career project. So thanks, Krishna, for the well-thoughtful introduction. So maybe I will bypass some of that. So in terms of my general research domain, I'm pretty interested in my research group to explore the general area of smart infrastructure, smart geosystem. So we try to break down the what smart constituent, indicate like sensors, structural health monitoring, now like AI, machine learning, big data, and also I call this active smartness. And then there's a smart functional materials, which described as passive smartness. So that's give how we can make geosystem to be or infrastructure to be smarter. And then infrastructure give a very broad domain of engineering practice, from geoengineering, from materials to infrastructure system. And then when we deal with this issue, we try to use like a system perspective to address the challenges, including inspiration from biology, bioinspiration. And also the fundamental goal is to improve the decision, make the infrastructure to be more sustainable and resilient. And this is my teaching practice, and also my mentoring practice. So involve a lot of PhD students, and also involve a lot of undergraduate students. I don't have a lot of master degree students so far, but I've just welcomed students to explore opportunity to work with our group, and also look for collaborations. Okay, sorry. So inside the motto I'm just to share is, I think there was a poem, or pretty famous, kind of over 1,000 years ago, talking about if we want to appreciate the beauty of a mountain, we just cannot stay inside. You have to stay away from the mountain to really appreciate the ground view and the beauty of the mountain, which is also very aligned with Case Western motto, the motto at Case Western Reserve University, was to think outside the box. So that's the essential typical notion I try to integrate into my group. Mostly my group consists of like a PhD student, and sometimes we also host undergraduate student and also high school student in research activities. So this kind of a recent photo when I took my group for a retreat. So after everybody shared the research, we enjoyed some happy time together. As a few group members was missing, but just this one captured pretty well the excitement. Every group member is passionate to explore innovation. So now go back to this particular topic. So this is the contribution to the work I introduced today. Was from 3 of my former PhD students. Symbol, who's at University of Texas Arlington right now. He was my first PhD student, and Julian currently at the Arizona State University, and Yuan Guo at the Sun Yat-sen University in south part of China. So this is kind of a brief outline of my presentation. So first, let me give a brief background about this challenge or impact of this resilience issue, and also talk about our multi-scale sensing and multi-scale simulation approach. Try to understand the fundamental and try to come up with a better solution. So, bridge scour refers to the phenomena when doing the flood event, the flood take the sediment away from around the bridge foundation. Consequently, bridge foundation, bridge pier lose the lateral support by the soil. Then in the extreme case, of course, bridges fail to collapse. So in the history, like I think this happened pretty over the world. In the U.S. history, essentially, this kind of incident by bridge skull is kind of frequently documented. And also, because of this kind of issue, so national bridge inspection standard require bridges need to be inspected every 2 years in the inspection frequency. And the fundamental issue is erosion, which is a kind of a involved a geotechnical process. So if you look at the failure of the bridges, the cause of bridge failure, like a bridge skull, the hydraulic reason of bridge skull, is responsible almost 60% failure. And also there's like other factors like overload, collision by ship or by boat. These are and also by earthquake, all these things come together, still a smaller percentage of contributing factor compared with bridge skull. So that's just illustrate the importance of this issue. And also this problem phenomena is also very complex because bridge skull, oh, I don't know why it's jumping. So bridge skull involves, involves like a complex interaction between fluid, soil, and structure. So involve the geotechnical engineering, hydraulic engineering, structural engineering. So essentially, it's a complex issue. And also the consequence is, you take the sediments around from bridge foundation and it like expose bridge foundation, make the bridge foundation be unstable, and which then impair the safety of the bridge. And from the practice side, like a bridge skull design, so essentially we need to estimate how deep the skull happens when a bridge is built, so that like design like a bridge foundation need to be sufficiently deep in order to take away the impact of bridge skull. And also, this kind of design equations are mostly from laboratory scale experiments. So they don't necessarily describe what's really happening in the field condition. And also, another important factor in the bridge skull design is to estimate how strong the soil resists to erosive force. This area for what's called a soil erosion model has been studied for a long time in the hydraulic engineer, in the water resource and environmental engineering area. So this kind of model is then typically in the practice that is extended to describe the hydraulic erosion happening with bridge skull. And the experience indicates the extension of existing model developed for the other purpose, like environmental purpose or water resource purpose, does not adequately consider the unique complex soil structural flow interaction during the bridge skull. So the model direct extension model has a limitation. And also the bridge skull essentially require also to estimate what's the erosive force by the stream flow, which is typically defined as maximum shear stress that's the stream generating on a riverbed. In the complex turbulence condition associated with bridge skull, this estimation can also there's a lot of uncertainty as well. And also in many practice, for the federal highway design equations mostly are based on one-dimensional, two-dimensional hydraulic model that's allowed to simulate the flow field and estimate the shear stress and then skull depth. So essentially, all these are kind of maybe from the engineering approximation as perspective, provide some guideline in the skull design and risk mitigation, but does not completely address the most fundamental issues, and also does not come up with most safe design and resilient design. So that's the practice gap. So the skull process essentially is a complex process. So for example, essentially, it's rarely happen. It's pretty rare. Like a skull just continue to go. So for example, build a bridge, they change the flow condition, generate the turbulence. The turbulence takes sediment away. The depth of sediment erosion typically is not like a smooth curve like this showing here. Most likely, they have a rippling effect. Like during the flood event, like we go to deeper skull depths, larger amount of soil got eroded, but during the retreat, flood retreat, sediment refilled back, settled down, refilled skull hole, and then another flood come in, this eroded again. So it's a repeating process. Like the current engineering practice for inspection every 2 years mostly happens after the flood event was over. So for example, like if this is a flood, the most unsafe condition, which is the deepest skull happens when during a flood. Well, the inspection maybe inspector maybe come back to inspect the bridge after the flood event, which maybe inspect condition corresponding to the smaller amount erosion condition. So that estimation might not like a safety address the safety issue during the extreme event. So that's a limitation of the current practice. So because of that, they require to capture. Okay, so essentially, ideally we should be able to capture the erosion and also backfilling process. But it turns out those will be pretty challenging. So that's a different practice to evaluate the skull, monitor the bridge skull. So for example, like the most common way, very common way is visual inspection. That's mostly happen like when the stream is relatively stable, like send a diver to dive under the water with camera or something to capture the skull, the shape of the skull hole, evaluate the bridge structure may be safe. There's also some instrument like this one. So mounted instruments which may monitor, install a camera or something, drop them down to the river and do a survey. And also there's some this one is actually the photo shot by a research group from Japan. So essentially, there's other manual measurement. You use it like the engineer use a yardstick to dig down the bridge abutment and find out how deep the sediment, the surface of sediment is as a way to determine the skull. There's also some monitoring device developed in the history of this research in this area. Like for example, using a very common one, like using like ultrasonics, for example, mount a ultrasonic sensor. The ultrasonic sensor wave travel down the bridge through the river water and reflect back, and then from the echo, the time lapse to hear the echo sound, we found out how deep the erosion happens. And also this is another one, use like a metal detector, essentially bury some metal which is on the surface of the river channel. And also when the erosion happens, they just drop down with the erosion, and then you use like a metal detector through the tube, inside of the tube, to detect where the metal is located. That also indicates the depth of the bridge skull. So all these instruments has advantage and limitations. For example, this ultrasonic acoustic-based measurement, they work pretty reasonably well during the clear water event, like when there's low much turbulence. The experience found like during the turbulence flow, like which happened during the skull, during the flood, like a lot of sediment in the river water, and also there's a little turbulence flow. They tends to attenuate the signal so that the acoustic signal will not be able to completely dissipated before they come back. So that's make it very hard to evaluate the most critical condition when the safety of the bridge is compromised, possibly compromised. And also, for example, for this using a metal detector, this one also only works if after flood event, when the condition is stable, so does not capture the the most unsafe condition. So essentially, sorry, I don't know. Yeah, so essentially, this study sponsored by Federal Higher Administration, because there's many bridges are subject to bridge skull, associated risk, and it's very expensive to rebuild the bridge. So essentially, the recommendation was install instrumentation to monitor the bridge skull would be a very important safety countermeasure. So under the financial limitation, this provide a way to assess the failure risk of a bridge and the flood event, provide safety warning, or they can like decision support, and become a cost-effective way as a skull countermeasure. And also just from the existing study side, for example, some regulation by U.S. Transportation Agency, for example, like Georgia, they require if the safety condition is uncertain, the bridge need to be shut down. So one case documented in the Federal High publication was like in 1994, there's a major flood in the state of Georgia because there's no instrumentation monitor the bridge condition associated with skull. So instead, because the uncertainty, the safety risk, so the state DOT of Georgia decided to close 1,000 bridge for inspection before reopen them to the traffic. So that caused a lot of disturbance to transmission network. So that's just to say like a benefits in-store bridge instrumentation to monitor the skull has some benefit. And then there's from the deployment of the skull instrumentation, what's required, for example, that's a mandatory criteria. So they need to be installed close to the bridge because most bridge skull, like one of the previous slides shows, skull hole most happen close to the bridge. So essentially, they must be able to install close to the bridge pier or bridge abutment. And also in terms of accuracy, we don't have to be scientifically accurate. So essentially, there's a tolerance about accuracy up to 1 feet. Will not compromise much the decision safety assessment. And also, ideally, the sensor need to monitor, be able to monitor the skull depth and remotely. So don't have to send the people down to the bridge foundation to do the data acquisition, and also be able to survive very large storm and flood condition. And also, there's some also desirable criteria for instrumentation that need be maybe it's not mandate, but just a desirable metrics. So there's some field monitoring tool, developing the history by Army Corps of Engineers, because they typically work with many bridge river conditions with very presented challenge. So for example, these are the summary instruments deployed in the field to monitor the skull hole. Again, this skull hole, like described, this most happen adjacent to the bridge foundation. So the key is to find out how deep the skull hole evolved. So there's a different technology, this one is what's called an instrumented fish. So essentially, this is like a shape, it's like a bubble, they are pre-buried under the sediment, under the river channel at a different preset depths. For example, every 1 feet, better one of them. And then this instrumented fish has a motion sensor and a radio transmitter. So what's when this, for example, is erosion, if the erosion happens, this instrumented fish will float. When they are exposed, they float to the surface of the river, and that a moment trigger the radio transmitter to send a signal to a radio recorder that's seated on bridge deck. So that then indicate how deep the skull hole evolves. So this instead provide a monitoring to determine the maximum skull depth during the flood event. And this instrument is just like a one-time use, so you can only deal with one flood, and another flood coming, you need to reinstall the instrument. And then there's another one. This is using a sediment chains. So the drill a hole into the sediment, put a chain in vertical direction at a different location along the bridge skull hole. When initially this chain will be vertical. If the sediment got eroded, the chain will fall down. So by a post flood, retreat of the sediment chain, can find out how deep the skull hole evolved during the flood. So instead, there's a lot of different studies of looking into develop instrument for skull hole assessment. As mentioned, there's also acoustic-based method, like a metal detector-based method. There also a remote operated boat to circle with acoustic sensor. They can remotely control and circle around the bridge pier to find out the skull hole. So these kind of instruments typically work pretty well in the steady water condition, and during the flood, there's a lot of debris come together with flood, make operation of this remote control the boat to be challenging under that condition. So there's also tools using a tractor articulated arm truck that's allowed to probe the skull hole depth while the inspector located on the surface of the bridge without having to access the bridge foundation and expose the personnel to the risk. So essentially, these are the stage of practice. So sonic sensor is the most popular, and then magnetic using the metal detector with a sliding collar second, and then the instrumented floating device was the third. So these are just the states of practice. So, and then I don't know, sorry, this automatic advance, so strange. So there's also kind of in recent years there's some a newer progress in the domain. I'm using fiber optic sensor mostly to monitor the structural stress development because the skull lead to changes the structural response, and also use there's another technology called smart rock. So it's a sensor that has a magnetometer located inside, and we encase into shielding that look like a rock. So the rock has a round shape, like a spherical shape. So the whole place during the flood, this rock always fell to the bottom of the skull hole, and then we can use a magnetometer to locate where the smart rock is located and then find out skull hole depth. So that's the new development. So this Army Corps of Engineer developed this, and also Northwestern University, they developed a time domain reflectometry based skull monitoring device. So this one is using a thin vertical cable with a blade, a blade, zoomed view of the blade along the cable. So when the skull happens, they expose the cable, expose the blade. The blade will be rotating, cause a shearing force on the cable. This one involves using guided radar wave sent down from the bridge superstructure. When the cable is sheared by the force, there's a reflection. So this one then allowed to detect using electrical wave, find out where the blades are exposed or where the erosion depths evolve. It's another one using similar time domain reflectometer radar, guided wave electromagnetic radar. So this involves send a signal is like echolocation principle in the bed. To send a signal that travel along the waveguide, when they say the waveguide see a difference in the surrounding material, like a water versus sediment, they generate reflection. And this one also allows to tell how deep the skull hole goes. Army Corps of Engineers tried this on a few, some river, because they have a cold region research office. So they installed this one in a river that's subject to icing condition. A challenge is, I think they work in monitoring skull depth, but one of the challenges, they were not able to survive very well during the icing event. When not ice moves down the river, they will just destroy the instrument. So this is the challenging condition for instruments for bridge skull, because during a flood, the stream can wash down anything. So it's kind of some extreme case, a lot of wood piles can pile up around bridge pier, which makes it very hard for instrument to survive, including the one Army Corps of Engineers developed. So we try to look into address this issue by learning from the strategy, mining a sea grass to survive very well, even under the most turbulent flow condition. because what they use, the strategy they use is rather than use a very strong pipe to carry the load, which can be smashed away during the flood by this big pile of debris. Like the seagrass, they have very bendable material, flexible material structure. When there's a very strong turbulent flow comes in, they just yield, let the flow pass. So essentially, inspired for that one, we just developed this kind of seagrass inspired sensing probe using the guided radar. So essentially, the principle for this monitoring device is to send the signal, the electric signal, which at the when it travels along the waveguide, is flexible waveguide. When they arrive at the water sediment interface, they will generate a reflection, and then at the end of the waveguide, they generate another reflection. So essentially, in principle, analyzing the signal reflection, we can identify how deep the sediment water interface or maybe the skull depth evolves. So this is the actual prototype we fabricated. So using this concept, so this is a flexible stripe made of inexpensive metal, a 3 parallel metal, and with a coating, and mounted on supporting structure. So the cost is pretty inexpensive. And in this illustration, the sensing capability. So with this stripe as a waveguide, like for the biostripe, they have a signal response like this solid line. And then if we put the artificial wet spot, so we put a sponge, a little bit drier sponge, and a sponge with a lot of water, and also this moisture tin with water. We see a waveguide. When the wave travels along the waveguide, they will generate like response because they see a different material. So we can see the 3 dips in the signal response. So this is an indication like the sensor is pretty sensitive to what happened surrounding the sensor probe. And if there's a change of the material condition, for the case is a bridge skull. Because bridge skull fundamentally evolves like a change from when the sensor installed in the river channel, the change that detects is the interface between the water and sediment, which is differentiable. So we essentially started by setting up laboratory scale experiment into the sensor probe, emulate skull depth at different conditions with different type of sediment, fine sand, gravel, emulate different sediment. We also try to clay, and also emulate different salinity condition, because the river water, they maybe have a lot of salt, so with a different condition. So essentially, we found a pretty encouraging performance in terms of detecting the skull depth or sediment water interface. And then based on laboratory study and because analyzing the signal can be like we essentially come up with a series to guide to analyze the signal, which identify the like what's called guided radar, electromagnetic radar, time domain reflectometry (TDR). The signal response is kind of linearly related to skull depth. So essentially, with this, like there's a algorithm development behind this one, but the end story is we come up with a simple way to interpret the signal to find a skull depth with a relatively simple relationship. Like this is very important for field deployment, because if we deploy anything in the field, we want the signal to be able to automatically analyze rather than manually interpreted. Because we can have a lot of signal from a field monitoring program. So with this as a basis, laboratory study, we then come up with field study plan. This system we deployed like a component used in a field monitoring system, from the stripe sensor, from the connection, the monitoring system, including power supply, to communication. So these are located in the field, and then this communication, cell phone data transmission to the office computer. So that's the system setup. So we essentially implemented that one together with Ohio Department of Transportation on one of their bridge. So essentially for this bridge have 7 bridge piers. So essentially we install 5 because this is a kind of a symmetric condition. So we try to assess how well they will work in the actual field condition. So with assistance from partners, like which include consulting companies. So what we did was we bring the machine because in the geotech engineering survey, if they do a bridge retrofit, rebuild a bridge, they typically do the drill hole to the river channel to sample the soil, do the geotech analysis to come up with a new design, foundation design. So we leverage a similar procedure. Our sensor is also designed to accommodate the hole, like drilled by this drilling machine in a regular geotech site mitigation. So this model, we essentially drill through the bridge deck, and then put a tube down, essentially drilling. That's the procedure commonly used for soil sampling in the site mitigation for bridge located all across the river. And then we deploy the sensors through the tubes under the river channel. After that, we fix the bridge deck. So, and then we install the instrument on the side of the bridge. So this is a monitoring box installed, which include the battery and also have a solar panel for long-term monitoring purpose, and also the controller, and also come to like a signal generator and a communication device to send the data to the cellular phone service, and then relay that one data to the office. So essentially, from the right after the installation, we see a system change in the signal response, which indicates that after the small probes installed in the ground, they disturb the condition of the riverbed, and there's a certain stage for the signal to become stabilized, and it caused a little bit erosion. And also this one, because the guided radar was able to get signal automatically, so it allowed to determine the skull process. So essentially, continuously. So essentially, we are able to capture skull development and backfilling process. And also, so we essentially capture both process, and also the bridge we studied has a river monitoring station. So that's has a river flow. So essentially, what we encounter results is the skull monitoring results we found corresponds very well from the river flow condition. So every time there's a flood, like a peak increase in the flow, stream flow, see more erosion, and afterward there's a backfilling process. So that's the kind of validation. The technology was able to capture both the erosion and the backfilling process that identified the skull as a dynamic rippling effect. And then on the other domain, we also try to understand the mechanism that's responsible for bridge skull. So essentially, during the bridge skull, because the disturbance of flood stream flow, the general flood turbulence, so vortex around bridge foundation. So erosion of sediment happens the first because the mag energy of the turbulence condition. The second is the resistance of sediment to the erosion. So both factors play a big role about how deep the skull hole will be developed around bridge pier and bridge foundation. Then turns out there's no good way to characterize the energy of turbulence flow. So in the mechanical engineering, they use like a hot wire technology. You essentially you put an electric resistant wire in the boundary layer and then blow wind, for example, to measure the turbulence flow. Essentially characterize how quick the thermal energy is loosed by the air to be dragged away by the air. That's why it indicates the energy, the turbulence energy. So for this one, the story is characterize. There's no good way to characterize the turbulence from the using sensor. And then for this part, essentially we got inspired by reading the literature from the biology. So there's a fish, very famous fish, called the Mexican blind cave fish. So as the name implies, this fish it does not have any eyesight, so it's blind, but it still survives pretty well. So then we were curious how it can identify the condition when they swim in the river. Turns out they have a very unique design with turbulence sensor. So on their lateral line. So essentially, what this one sensor does is they generate when there's a disturbance to the what's called health cell on the lateral line, they will generate electric conductance, generate electric signal, neuron signal that allow the fish to detect. So if conceivably like this one, so like if a flow comes in, disturb the like a health cell sensor along the lateral line, they generate a neuron signal, and there's a delay, the neurons time delay in the neuron signal, because the flow take a different time to arrive at a different health cell element. So by determining the travel time difference, like when the neural signal is produced, and also they have like maybe from the neural network calibration, they already know the distance. So they can identify a turbulence flow that's coming towards the fish themselves. So without even be able to say something. So for example, if there's a predator coming for the fish, they will try to escape because they were able to detect how fast the turbulence flow is coming. So inspired from this one, we actually looking to replicate this bio-inspection to develop a sensor that be able to detect how fast turbulence flow is moving. So essentially, we come up with a design. Essentially, with this one, we design emulated the bio health cell sensor. So essentially, this is a different generation we produced in the lab. So the goal is the actual sensor is pretty small, in like in the micron in the length. We use a larger structure to capture the disturbance. So essentially, the evaluate this sensor, we essentially like for example, this sensor is under the disturbance of the structure, they generate a signal response that's allowed to detect the disturbance. So essentially, this is a concept. It's from the setup we did. So we mounted the artificial health cell sensor on angle controller, and then we disturb the like a band, in deflect the health cell sensor and see the signal response. And see like so we bend this one to a fixed distance. You can see the signal response from the sensor. So this one, and another very unique feature for the biology sensor is they have a directional sensitivity, which means at a different direction they have different magnitude response. So maybe to summarize the result, it's like we were able to find like a design of sensor, artificial health cell sensor that have a signal response very similar to what's observed in the biology system. They have a different sensitivity in different direction. Like 0 degree, 90 degree, 180, 270, they have different response. This one essentially allow to reproduce biology sensor and then come up with a sensor that's allowed to directly characterize the magnitude of turbulence energy. So so another important part for erosion mechanism is the turbulence flow. So characterize the turbulence flow and the soil erosion resistance. So actually, our goal actually, which is kind of still ongoing, have not completely accomplished, is to be able to come up with multi-scale simulation, like from the stream, like a microscopic scale, study the stream structure, sediment interactions, generate the flow field, and integrate that one with a turbulent like a erosion model, soil erosion model for soil particles, and to be able to directly predict the skull condition. So that the sense of the process is also pretty complex. So this is the workflow for that process, which is required to determine the flow field, determine the shear stress, and which also consider the turbulence condition to determine, in the end, to determine the skull depth when the shear stress and the resistance are balanced out. So essentially, for implement this kind of multi-scale simulation, we then need to understand, like to be categorized what fundamental resistance to soil particle from the detachment by the erosion force by the stream, which turns out also pretty challenging. So for that part, we leverage is with a discrete element model combined with computational fluid dynamics. So essentially, this is some example. Let's say to first, so this like a self-DDM, computational fluid dynamics and discrete element model, they come together to be able to simulate flow condition and also simulate how the particles interact with flow. So this is the to ensure the results are reliable. First, need to validate the performance. So essentially, we use like this is one example, like say a pile of particles settle down, deposit into stationary water. What's the angle, like a ripples angle to form? We physically measure that one and use a CFD-DM to simulate that condition and direct with a simulated angle and the direct measured angle, with as a first step to validate the model performance. And with that one, essentially we can simulate the flow conditions. You know, like this one, like erosion process. If there's a pile of sediment, for example, in this case, inside a pipe, if the flow comes in, like how the erosion process looks like. So this is essentially, so the strength of self-DDM essentially allow to simulate particle erosion process directly. That's from a fundamental microscopic perspective. And also, if we consider the turbulence, so the two cases shown here, this one is only have laminar flow. If we consider the turbulence energy, essentially the erosion happens much faster, which is also validates why, like during like flood, during the skull hole can develop pretty deep because the turbulence energy make a big contribution to the erosion. Also, like Professor Jean-Louis Brown from in Texas A&M University has a famous erosion functional device that's allowed to categorize the erosion resistance for sediment for different type of soil. We use a virtual simulation experiment. So in generate particle different shape, and then emulate like a experimental condition to study the erosion rate at different flow condition, different particle condition. So essentially, this one allow to directly determine what the soil erosion resistance, the soil erosion resistance curve. So for many soil, unless it's a round-shaped soil, like round-shaped particle like this one, any flow will make the particle to be eroded, start to be eroded. For particles has angularity, it takes there's a what's called a cutoff water flow velocity. So under this velocity, there's no erosion. Only the erosion won't happen if it flows above the cutoff flow velocity. So like simulation allows to directly validate this one. So with this in mind, then now we characterize the erosion resistant behavior of particles and also study the overall river flow condition. Then we can put them together as multi-scale case, then allow to guide the design of bridge foundations. For example, if like a round-shaped bridge pier with a bridge pier with a different shape, when there's a mingling of the stream, they maybe during the flood, water maybe come at different attack angles than what they are initially designed for, how they would affect the erosion condition. So this essentially, common kind of simulation allow to determine the flow field behind the bridge pier, and also from the flow field combined with the soil erosion, then provide more realistic about what skull hole shape will look like. So this is just a kind of a little bit details, because simulation from the flow field allow determine the shear stress and that consider turbulence under the surface river channel that combined with soil erosion resistance, then allow to determine the skull hole, realistic skull hole shape. And from that one, you can come up with recommendation. How, for example, for example, the British pier may be designed for 0-degree attack angle. Like when normal condition, the water flow comes just parallel to the direction of the bridge pier, but during the flood, they may come from the other direction. So essentially, from this study, we were able to come up with improved recommendation on how to design bridge pier to consider the stream might come from different direction in the flood compared with the normal condition. And then the other engineering implication is with this predictive capability allow to deploy the right countermeasure for risk mitigation. So based on the shape of the skull hole, so very common type of countermeasures using riprap, which is like a big size boulders dumped around bridge foundation, to protect, to mitigate the soil erosion. And then then there's the issue how extensive this material, what the size need to be used, what area need to be protected. All this can benefit from input understanding of erosion condition. So maybe I run all the time. So essentially, let me a brief summary. So essentially, bridge skull remains one of the most challenging issues for affecting the resilience of a bridge and also transportation network. So structural health monitoring is an important approach for risk management, and it can help improve decision support to ensure the safety of the bridge and in kind of a cost-effective way. And then from the fundamental understanding, turbulence is an important factor for bridge skull, new sensors, new simulation tools, and this is kind of require further research, can potentially provide a good way to address these kind of challenges. And also to study this kind of topic requires bring in together interdisciplinary strategies to come up with a better solutions that improve the resilience and safety. Okay, finally, maybe try to give a little bit description, introduction of our geotech engineering program at Case Western. So I don't know if anybody's familiar with pile driving. So in pile driving, very popular method for the Case method. So actually, the Case bears the name of Case Western with our home institution. The pile driving technology was invented by 3 pioneers at Case Western. George Goebel, who's a professor, and also 2 of his PhD students, graduate students. One is PhD student, Frank Rausch. The other is master degree student, Garland Likens. So 3 of them, the co-inventor of the technology. They subsequently founded a company, Pile Dynamics, which is a world-renowned company for construction quality control in the deep foundation. And also, a case our professors have been pioneering in understanding the anisotropic behavior of soils, the fracture mechanics of soils. This by Professor Tony Sutter, who retired last year after 60 years service, 60 years of service to the university. And then a newer generation, relatively newer generation, who use study a lot of centrifuge, like Professor David Zhang, who left our department to become vice provost. He was an expert in the centrifuge testing, and then me and most focus pretty broad range of topic of multi-physics, multi-scale problems. And we have a new professor, Professor Su, Yong Su, joined us this semester actually. He's an expert in the machine learning for computational mechanics. And also, department-wise, we have built an excellent research infrastructure. So essentially, let me just say we welcome potential to host researchers who are interested to stay at our university for visit or for other form of collaboration. So finally, I want to thank my research group, funding agency, and the department colleagues for the support. Okay, thank you very much.
Yeah.